Let me start with a simple question. Every one of us trusted the brakes of our car, the autopilot in a plane, the infusion pump beside a hospital bed, or even in a ventilator. And no one of us has ever read their source code. We trust the machines we never inspected every day. That trust doesn't happen by luck. It's engineered and deliberately layer by layer. And international standards are the reason it holds. So for the next few minutes, I'm not going to read you the catalog of standard numbers, but we are going to do something better. Design one real machine together. A robotic sort and packing cell. I'll call it as SmartSort. And watch a standard appear at every layer from the raw steel to its firmware. My promise to you, by the end you will stop seeing standards as paperwork and start seeing them as the line between a product that ships and the one that hurts somebody. So let me introduce you to SmartSort. Picture a compact industrial cell on a factory floor. A 6-axis robotic arm works alongside a VN guided delta picker, both moving over a running conveyor. Together they sort and pack about 1200 items every hour, that is one item after every 3 seconds, all day, every day. Behind safety guarded inside a sealed IP54 cabinet, talking over a zoned industrial network using PROFINET. Now look at the 4-number block on the left. They are the roadmap: mechanical, electrical, electromechanical, software, and cyber. The slides ahead open up each of these boxes in turn, and for each one I'll show you the complete engineering process step by step with the standard that governs at every step. And hold two figures in your mind. They come back: the safety rating PLD, SIL2, and that one word in the network zone. From this point, every standard I mentioned has a real physical home inside that one machine. No more abstractions. Layer 1 of SmartSort. And we start with steel, not software. That is deliberate. The first line of the safety defense is always physical. Take a look at the layout on your left side. The servo conveyor, the VN guided delta picker overhead, the 6-axis robot, and the guiding around all. Every one of these elements exist on this sidelines process. So let me walk through the 6 stages to show you how each standards actually makes us do. Stage number 1, risk assessment. Under ISO 12100, before a single part of SmartSort is molded, the standard makes us define the machine's limit, how operator will use it, the space it occupies, its whole lifetime, including cleaning and jam clearing. Then we hunt hazards systematically. Crushing point where the conveyor meets the frame, shear points which are at the gripper side, and the robot's entire reach envelope. Each hazard gets a risk score from severity and probability. And ISO 12100 prescribes the order of attack. Eliminates by design first, safeguard second, warns last. The output is a living document, the root of the entire SmartSort project. Stage number 2, concept and structural design, controlled by ISO 9001. SmartSort's frame, kinematics and load paths are recorded as design inputs and outputs. Every review is minuted and no change happen without formal control traceability. And here the traceability decisions are included in the design process. And then the stage number 3, detailed design with ISO 101 and ISO 2768. This is how our drawing becomes unambiguous. Positions and flatness tolerance on the critical fits, general tolerance on the rest. It is the reason a bracket machined in one workshop bolts perfectly onto a machine welding in the other workshop. Stage number 4, strength and fatigue verification. 1200 items an hour means millions of load cycles a year on that conveyor, so we can run finite element analysis against the dynamic loads and prove the safety factors. Those results feed straight into the risk file as an evidence. Then the stage number 5, the guiding, or you can say the guarding you can see at the left of the illusion, and here two standards works as a pair. ISO 14120 that governs the guard themselves, rigid structure, fixing that needs a tool to remove. ISO 13857 governs geometry. Its table dictates from the size of every mesh opening exactly how far the guard must stand from the hazard, so a hand can never reach through in limit. Stage 6, manufacturing and inspection, closing the loop under ISO 9001, welding inspection, dimensioning report, material traceability. But this perfectly safe structure just sits there until we give it power. That's our next layer. Layer 2 of SmartSort, power and its invisible enemy, noise. Look at the illustration. The IP54 cabinet on the left is the heart of this layer, and follow the chain. A 24-volt control signal leaves the cabinet, energizes the solenoid valve, and the valve poured compressed air to the pneumatic cylinder that opens and closes the SmartSort gripper. Electrical control becoming physical grip. That whole chain is engineered under standard that are basically described on this slide. The backbone is IEC 60204. And watch how it opens and closes the process. Is tell us how the design of the system works, and then how to prove we did it right. Moving to the stage number 1, the supply and load design. IEC 60204 makes us calculate SmartSort's full load current, select the incoming supply, and fit a lockable main disconnect. So a maintenance engineer can isolate the cell and padlock it dead before reaching inside the cabinet. Stage number 2, protection and earthing. IEC 60204 works with IEC 60364. Overcurrent protection is coordinated so the nearest device trips first. Every conductive path of the cell, frame, cabinet, conveyor is bounded into one equipment that is basically connected over the network. So a fault has a guaranteed low impedance path home and the breaker clears it in millisecond. Stage number 3, the cabinet itself. IEC 61439 treats the switchgear assembly as a verified product. Temperature rises, short circuit withstands, and clearance are proven, not assured. And IEC 60529 gives us the IP54 rating. Dust and the splash protection and proof. Chosen for the SmartSort's real factory environment, not the brochure photo. Stage number 4, wiring and EMC under 61000, IEC 61000. Power and signal cables are segregated, shielded, terminated properly. Why does it matter so much? Because this is the true cyber physical twist. Noise that corrupts an encoder or a valve instantly become a physical fault. A gripper that fires at the wrong moment can completely destroy the system. Moving to the stage number 5, the protective devices. SmartSort light curtains are built to IEC 61496, and for our PL and for that we are basically using PLD application that must have type 4, the highest class, that are basically able to detect their own internal failures. Stage 6, verification, and straight from clause 18 of IEC 60204. Protective bounded continuity, insulation resistance, and the dielectric test. Each recorded in a single report. The standard does not let you claim safety. It makes you measure it. Clean, protected, proven power is still just potential. Next, we turn it into motion. And that is where the part 1 ends, deliberately. At the moment, the machine stands completely but lifeless. Think of the SmartSort we already have, a frame which is basically guided and designed under the ISO 12100 risk and the safety measures, and an electrical signal that is basically designed into a complete safe system. But right now nothing moves. There is no torque, no logic, no intelligence. A body without a nervous system. In part 2, we will bring it to life. We turn electrical energy into the controlled motion with drive integrated safety function. We give the machine a brain, discipline, and the embedded software. Then we follow the two threads that cuts through everything. Functional safety down the arithmetic of PLD and SIL2, and the cyber security under IEC 62443. And we finish where every real project must finish, the CE mark and the new machinery regulation that arrives in January 2027. Part 2 is linked right below to this video. I'll see you there.